Okay, I'm going to record some podcasts from this book. Let me adjust the volume here. Okay, from this book by Andy Robertson at Columbia University, the International Research Institute for Climate and Society, I think is the current name, and Frédéric Vittard from France. They have been leading these global efforts under the World Climate Research Program's S2S project, Sub-Seasonal to Seasonal Prediction Project, which is now seen as the key timescale to build early warning systems, which in fact can serve as adaptation tools for many countries like India, which is experiencing a lot of climate change embedded into climate variability, like the large-scale monsoon extremes, heat waves, etc. So you don't have to always think of climate adaptation as something long time scale. It's something that can be done as adaptive management on sub-seasonal, which is less than one season. If you think of season as 90 days, this is typically time scale less than 90 days, and we'll see that the terminology comes from some processes that occur at these time scales. So it's going from weather time scale, there is a climate time scale, and this is kind of a bridge in between. You can think of weather as short, medium time scales of 1 to 3 days and 3 to 10 days, and then climate is, let's say, seasons to years, or even decades, and the subseasonal is basically generally talked of as week 2 to 4. So subseasonal to seasonal actually includes week 2 to multiple seasons and years. There is also a new terminology evolving called societally relevant timescales. This is something to fill in, as I will show in a minute, the timescales of where weather prediction was and where IPCC came in, and where ENSO prediction was, with a big gap in the subseasonal timescale. So sorry about that, I made a little pause there to add a figure. So if we think about the timescales, here is the impact-based decision support, which is how NOAA thinks about it, from timescales of preparation to response to recovery, approximately. We'll see another way of putting this a little bit later on. And there is the forecast lead time, where you have timescales, let's say, going down this way corresponding to this direction. Climate outlooks, seasons to multiple years, let's say, including projections. Climate predictions, which are, let's say, El Nino timescale. If you don't know what El Nino is, you can go and look at my podcasts related to those. Weather forecasts, which you know, and then warnings. So the advances in weather predictions have been now well documented. We'll see a little bit more. As I said, it's short to medium term, so days 1 to 3 and 3 to 10, and there have been boundaries pushed towards day 10, as we will see. This is very widely used by all kinds of businesses, governments, disaster management, airlines, tourist industry, etc. And then IPCC came along and started putting out lots of information on multi-decadal to century timescale information on how temperature warming will happen, how extreme events will change, how sea level rise will happen, how crop yields will change, how fisheries will be affected, and so on and so forth. And you know that there have been lots of debates, and there continue to be debates about what to do with this information at such a long time scales, and what are the ways to account for the uncertainties in the scenarios that are used to make these projections. But in general, there has been what is considered a useful environmental prediction timescale in the middle, going from weather to this timescale, which is the subseasonal to seasonal timescale. So we will talk about how this is related to initial conditions, and this is boundary conditions. Some of you may have already heard about Ed Lorenz's chaos idea, where weather can get chaotic after a few days, and yet there are ways to make predictions beyond that. Where does this predictability come from? That's always kind of the key question. In the meantime, the weather prediction skills themselves have improved tremendously for both the northern hemisphere and the southern hemisphere. Typically, the lag in the skill of the southern hemisphere, which is the lower line in each of these, has been because of lack of data, especially over the ocean, because the southern hemisphere has much more ocean than land compared to the northern hemisphere, which has much more land, where lots of data have been collected over years, over decades in fact. So the forecast skill here is shown in percentages, and the time horizon from 1981 to 2014 or so is shown here, and you can see that both hemispheres have improved. Southern hemisphere has caught on much faster at day 3, day 5, day 7 and day 10. Obviously the skill drops off as you go to longer time horizons, and there are also differences between mid-latitudes and tropics, because mid-latitudes have large-scale synoptic systems order 1,000 kilometer, which stay for order day 10 days, whereas in the tropics you have convective systems which fire up very quickly and make predictions beyond day 3 quite difficult. Okay, so there is a hemispheric asymmetry and there is a latitudinal skill difference, which all have to be considered. So these are the kind of ideas we will look at some more details on weather prediction and climate prediction, and then where the evolution of subseasonal to seasonal forecast came from, and what have been the user demands. So once you start providing prediction information, people demand more. For example, countries like India, which only more recently started making very routine dynamic forecasts at weather extended range, which is the subseasonal to seasonal and climate predictions. Now people are ready to criticize the lack of skill, which is how operational centers try to improve the predictions as well. Once you start issuing information, for example, to farmers, they will tell you that that information was not useful or that it was just plain wrong. So then you have to keep on talking to the users and make your prediction skills get better. How do they happen? We will see some of those details.